To explore the new PrimeTurning technology from Sandvik. So in this demo, we'll show you what you need to do to use NX-CAM to create the specialized toolpaths that are required to make PrimeTurning work correctly. Because it's a new technology, I'm going to start with a few slides to introduce the important factors to making this technology work. But it will be a quick overview. There's a lot of information out there on the web right now, including in the June issue of Modern Machine Shop, a pretty extensive article. So let's get started with our overview. Here are the A and B variants used with the PrimeTurning system. A is obviously a smaller insert, gets into tighter spaces, a little more restriction though on the feed rate and depth of cut that are possible. B, a much better choice for roughing. These are non-ISO inserts, although they sort of look like ISO inserts, but you can see there's a compound angle on here. For instance, on the B variant, there's a little wiper that's formed here on the edges. This slide shows a comparison to conventional turning in blue, the PrimeTurning in red, whereas on this corner, if we were doing conventional, we'd be going into the corner, down the face. We're going the opposite direction with PrimeTurning, and that is essentially to take the load off the nose of the tool. So our chips are going to be formed here on this edge. By using this small leading angle here, we move or spread our chip load out over a wider area of the cutting edge, making it last longer. Now, many of us who have used manual lathes in the past have taken an insert of this type and run it backwards, and it does cut, but usually what we find is you're going to get chatter and you're going to get long stringy chips. So the Sandvik people then have solved those problems and other problems with this insert technology. Just a review then, you see a substantial difference in the depth of cut and a slight improvement here in the feed rates that are possible. But beyond that, though, you can cut your tool changes and just the number of tools you have to have loaded because of the flexibility of this insert to handle a wide range of different geometry types. Similar situation with the B variant. We're cutting here in the opposite direction, and in this case we've got pretty similar depths of cut, but the feed rates are substantially different. Here are test results for the A variant, the conventional insert at 13 minutes. You can see it took 57 minutes to create a similar wear on the A variant. Here's the B variant at 18 minutes. The conventional insert's worn out. We're still running at 100 minutes with the B variant. This is also a real nice view of the chip breakers and that compound angle with the little wiper here at the bottom. So let's review what makes this technology successful. It's those small entering angles that allow the chip to be formed on a greater area of the edge. We're protecting that corner. We're saving time, tool changes by using the same tool for roughing and finishing, and we're able to get into more areas of the part. And the chips aren't jamming up in the corners because we're moving away from the corners. Here's that entering angle in more detail. You can see how the wear then is concentrated on the edge and not the nose of the part. So PrimeTurning can offer a lot of advantages, but we want to carefully select the jobs and situations where we use PrimeTurning. We're looking for rigid components and parts of components. We need machines that are rigid, where we've got a lot of torque and horsepower. And if our length to diameter ratio is large at all, we need a live center or a tailstock on that part. So here's some parts off to the left side that are going to be more suitable, and parts off to the right side we see the long thin part with no live center. That's not going to be successful with PrimeTurning. And here's some actual images of some parts that you can successfully turn using this technology. At this point, let's move back to NX and do the demo showing the actual toolpath creation. There's certainly a lot of videos out on the web right now showing this PrimeTurning technique, and it appears that when they're cutting into a corner like this, they're just plunging right in. But if you can look closer, actually they're not doing that. If we plunge in, what we're going to do is break that nose of the tool down really quickly, which is what we're trying to avoid. So in fact, to make the prime turning technique work successfully, we've got to add a little arc and enter the workpiece tangentially. But we need to do something else. We've got to slow our feed rates down as we're doing that lead in. So we can see here on the screen, I should point out this is our teach mode, and some of it's kind of going off the top of the video here, so let me fix this. So you see the feed rate right here in yellow. We're going to begin, here's our traverse move, the dash blue. Here's our engage move in yellow, and that's 0.012, 12 thousandths of an inch per rev. And that feed rate's going to continue down into this larger arc. That gets us engaged. Then we switch to our cutting feed rate of 20 thousandths of an inch per revolution. But then as we get to the end, we're going to do something a little different, and I probably got this exaggerated a little bit, but we need to slow the feed rate down before we get to the end. And when I say exaggerated, I mean it didn't have to be this far back. I was just trying to indicate that we do need to make a transition back to the 12 thousandths of an inch per rev feed rate before our cutter exits the part. Now we're just looking at the cutter path itself. Let's verify now so we can see the actual tool. Now if I switch back from tool to assembly, you see our ISO insert. So this is the way we can create the tool path using an ISO standard insert, but then when it's time to simulate and validate, we want to switch back to the assembly so that we see the actual shape of that B variant tool that we're using for this tool path. Okay, so I've just got something really simple here. We're trying to cut into this corner and rough some material away. So let's go back now to the entire program, and let's toolpath verify. So these are just 3 passes successfully deeper. We've got it switched to 2D material removal, and let's play it. So our lead-in move, although it, going real quickly, it appears to be plunging. We're actually arcing in, and again, the objective there is to preserve the nose of the tool. We're slowing down for those 2 arcs that you see. We speed up, and then before we get to the end, we do need to slow down again before we exit the cut. Those are the main criteria that your toolpath needs to have so you can be successful with prime